Hello there, and welcome back to 5 Minutes Fall to Sleep. Before we begin, find the most comfortable position for yourself. You may be lying on your bed with a soft pillow supporting your head. You may be sitting with your back resting on a cozy sofa. Wherever you are, allow your body to sink and relax completely. Let your shoulders drop away from your ears. Let your neck rest. Let your hands settle gently and naturally in whatever way feels most comfortable for you. If this is your first time visiting the channel, or if you are looking for better sleep supported by science, press subscribe and turn on the notification bell. Each night, we have a new story to help you relax, to help you explore, and to help you drift into peaceful sleep together. We will travel from the first moments of the universe, when everything was blazing and scorching, to the enormous structures stretching across billions of light years. We will meet tiny particles passing through your body every second without your awareness. We will learn about the invisible forces shaping entire galaxies. And finally, we will look toward the distant future of this universe. Do not worry about remembering everything. Simply listen. Let your mind drift. And if you fall asleep halfway through, that is the best outcome. Close your eyes. Or if you are not ready yet, let your gaze rest softly on a point without focusing. When we think about the early universe, most people imagine darkness, an empty, cold blackness waiting for something to appear. Perhaps because we are used to darkness coming before light. A dark room before we turn on the lamp. A night sky before the sunrise. But the reality of the early universe was the complete opposite of that intuition. The early universe was not dark. It was unimaginably bright, brighter than any star, brighter than any supernova. So bright that light filled all of space, and the boundary between light and matter became blurred. Let us go back 13.8 billion years, back to a time when no stars were shining, because no stars yet existed. No galaxies were spinning because galaxies had not formed. No planets were orbiting any star. There were not even atoms, not even molecules, not any complex structure familiar to us. Everything in the current universe, every particle of matter, every ray of energy, every photon of light, all the substance that makes up the hundreds of billions of galaxies we can observe, was compressed into an extremely tiny space, smaller than the tip of a needle, possibly smaller than an atom. The density at that moment cannot be described by any example from everyday life. If you compressed the entire Earth to the size of a grain of sand, that density would still not equal even a billionth of the density of the early universe. The temperature was beyond belief. Not thousands of degrees like the core of the sun, not millions of degrees like an exploding star, but trillions upon trillions of degrees Celsius. A number for which nothing on Earth, nothing in the solar system, nothing in our entire galaxy offers a meaningful comparison. At that temperature, nothing could exist in any form we know. Molecules, the building blocks of all complex matter, could not survive because the heat would instantly break the bonds between atoms. But even atoms could not exist. Electrons, the tiny particles that orbit atomic nuclei, had too much energy to remain bound. They flew freely, unattached to any nucleus. Even protons and neutrons, the particles that form atomic nuclei, could not maintain their structure. They broke apart into their smaller components, called quarks and gluons. These are the most fundamental particles we know, the final building blocks of matter. The universe was a sea of quark-gluon plasma, a dense soup of fundamental particles moving chaotically at nearly the speed of light. In that plasma, light existed in the form of photons, particles with no rest mass but carrying energy. Photons were born from collisions between particles, from reactions between matter and antimatter, from the very energy of space itself. They existed for a brief moment before being absorbed by another particle, releasing energy, then being created again through another interaction. This cycle of birth and destruction happened at unimaginable speed, billions upon billions of times every second. Light filled every point of space, but it could not travel far. Imagine standing in a thick fog on an early morning. Sunlight tries to pass through, but it is scattered by countless tiny droplets suspended in the air. You can see light all around you, and everything has a pale grayish brightness, but you cannot see more than a few meters ahead. Light cannot travel in a straight path because it is constantly being blocked and redirected. The early universe was like that, but denser than any fog by an unimaginable factor. Photons tried to travel, but in a billionth of a second collided with an electron or another charged particle in the plasma. Each collision changed the photon's direction, bouncing it off into an entirely new path. Then it traveled a tiny distance, perhaps only the width of an atomic nucleus, before the next collision. Another redirection, another tiny movement, another collision. If you could track the journey of a single photon, you would see it follow a twisted and winding path, like a drunken wanderer staggering through darkness. That photon could take thousands of years just to travel a distance equivalent to a few meters in today's space, because it was bounced back and forth countless times. Light was imprisoned. It could not escape. It could not travel far. It was trapped within the very structure of the universe, like a prisoner inside an invisible cage. In that state, when light was so dense it could not move freely, it began to behave not like light, but like matter. In daily life, we think of light as something gentle and weightless. We can walk through a beam of light without feeling any resistance. Sunlight shines on us without pushing us backward. But light carries energy. According to the famous equation E equals mc squared, energy and mass are two expressions of the same thing. Energy can be converted into mass, and mass can be converted into energy. When the energy density of light is high enough, as it was in the early universe, light can exert real pressure, push matter, and bend space around it the same way a large mass does. The early universe was a place where the boundary between light and matter was blurred. Photons could collide with each other to create particle-antiparticle pairs. Particle-antiparticle pairs could annihilate each other and turn into photons. Matter and light were not two separate things, but a single entity constantly converting between forms. Physicists call this state the radiation-dominated era, a period in which energy in the universe was primarily in the form of radiation rather than matter. Light was not something illuminating matter. Light was the dominant component of the universe. But nothing remains in that state forever. The universe is expanding. And this is one of the deepest truths about reality. Space can stretch, increase in size, and create more space where there was once less space. With every thousandth of a second that passes, space expands. The distance between particles increases. The density of the universe decreases. And as space expands, energy becomes diluted and the temperature drops. This principle is similar to what happens when you release a can of compressed gas. The gas expands to fill a larger volume, and as it does so, its temperature decreases. You can feel this if you have ever used a compressed gas can. The nozzle becomes icy cold. The universe cooled in a similar way, but on a scale vastly larger. Within the first second, the temperature dropped from trillions upon trillions of degrees to billions of degrees. This happened extremely quickly. In the earliest fraction of the first second, the universe expanded at a nearly unimaginable rate called inflation. During inflation, the universe may have increased in size by 10 to the power of 26 times or more in only 10 to the power of negative 32 seconds. This was expansion far faster than the speed of light. This may sound like it violates Einstein's theory of relativity, which states that nothing can move through space faster than light. But here, nothing is moving through space. Space itself is stretching, and there is no limit on the rate at which space can expand. Imagine drawing two dots on a deflated balloon. When you inflate the balloon, the distance between the two dots increases, but the dots are not moving across the surface. They remain fixed in place. The surface itself is expanding and carrying them along. The universe expands in the same way. Particles of matter are not moving through space faster than light, but the space between them is increasing, and there is no limit to that speed. As the universe expanded and cooled, physical processes began to change. The energy of particles decreased. Collisions became gentler, and at certain temperatures, important phase transitions occurred. Within the first few seconds, while temperatures were still at billions of degrees, quarks and gluons began to bind together to form protons and neutrons. A proton consists of 3 quarks, 2 up quarks, and 1 down quark held together by gluons. A neutron is similar, but contains 2 down quarks and 1 up quark. This was the moment when atomic nuclei began to form. After about 3 minutes, when the temperature had fallen to about 1 billion degrees, the conditions became suitable for nuclear synthesis. Protons and neutrons collided and fused, forming the first nuclei heavier than hydrogen. Most of these became helium nuclei containing 2 protons and 2 neutrons. A small fraction became deuterium, lithium, and beryllium. But this process lasted only a few minutes before the universe cooled too much for nuclear reactions to continue. As a result, after the first few minutes, the universe contained about 75% hydrogen and 25% helium by mass, with a very small amount of other light elements. and this ratio has remained nearly unchanged in regions of the universe, not altered by later generations of stars. But even though nuclei had formed, the universe was still a sea of plasma. Electrons still moved freely and were not bound to nuclei. Because of this, light remained trapped and could not travel freely. It would take hundreds of thousands of years for the next important event to occur. When the universe reached an age of about 380,000 years, the temperature had dropped to about 3,000 degrees Kelvin, which is about 2,700 degrees Celsius. This was still extremely hot, hotter than the surface of many stars, but cool enough for something remarkable to happen. Electrons, once moving freely with too much energy to be captured, had now slowed enough. They no longer had enough energy to resist the pull of positively charged nuclei. An electron passing near a proton was captured by the electromagnetic force. It began to orbit the proton, forming the first hydrogen atom, the simplest of all atoms, consisting of one proton and one electron. Around helium nuclei, which contain two protons and two neutrons, two electrons were captured, forming complete helium atoms. This process, called recombination, occurred throughout the universe in a relatively short time. Within tens of thousands of years, most free electrons were bound into atoms. The plasma disappeared. The sea of free charged particles was gone. Instead, the universe was now filled with electrically neutral gas made of complete atoms with equal numbers of protons and electrons. For light, this changed everything. Photons interact strongly with free charged particles such as electrons, but they interact only weakly with neutral atoms. A photon can pass through a cloud of hydrogen gases with almost no effect unless it has exactly the right energy to excite an electron to a higher energy level. When electrons were captured into atoms, the path for photons suddenly opened. The obstacles vanished, and for the first time in 380,000 years, after hundreds of thousands of years of being trapped in the dense plasma, photons could travel freely through space. Light was released. Imagine what that would feel like if light could feel. After an unimaginably long time trapped and colliding billions upon billions of times every second, unable to travel farther than the width of an atom before being blocked, suddenly there were no barriers. The path was open. Freedom. Photons rushed forward in straight lines, unobstructed and unbent, flying through space at the speed of light, which is 300,000 kilometers per second. And from that moment, 13.8 billion years ago, those photons have been traveling continuously without stopping through the vast distances of the expanding universe. Some traveled into regions that became the first galaxies. Some drifted through the empty gaps between galaxy clusters. And some, a very special few, traveled for the full 13.8 billion years and eventually reached a telescope on Earth, where they were detected and studied by humans. We call this light the cosmic microwave background, or CMB. It is one of the most important discoveries in the history of science, a direct window into the early universe. When these photons were first emitted 380,000 years after the Big Bang, they had high energies corresponding to a temperature of 3,000 degrees Kelvin. They belong to the visible part of the spectrum and may have appeared as a bright reddish-orange glow like heated metal. If you could have stood there at that moment and looked around, you would have seen a uniform brilliance in all directions, a sky glowing brightly without stars or galaxies, only pure light. But the universe has expanded by more than 1,000 times since that moment. And as space expands, the wavelength of the light traveling through it is stretched as well. Imagine a wave drawn on a rubber band. When you stretch the band, the wave is stretched and its wavelength increases. A photon experiences something similar as space expands around it. Visible light with a wavelength of about 400 to 700 nanometers is stretched into infrared light with a wavelength of several micrometers. It continues to stretch into microwaves with wavelengths of a few millimeters. Today, 13.8 billion years after it was emitted, the light from the early universe has become microwave radiation with a wavelength of about 2 millimeters and a temperature of only 2.7 degrees Kelvin, which is minus 270 degrees Celsius, only about 3 degrees above absolute zero. It is very cold, but it is still there throughout the entire universe. You cannot see the CMB with your eyes because it lies outside the visible spectrum. But if you had a microwave telescope or even an old radio tuned to the right frequency, you would detect that the entire sky is giving off a uniform, gentle microwave glow from every direction. In fact, if you have ever seen static on an old analog television screen with no signal, about 1% of that noise is caused by the CMB. You were seeing the echo of the early universe. It is the light from when the universe was only 380,000 years old, now aged for more than 13 billion years, but still present, still quietly passing through space and carrying precious information about the conditions of the universe when it was very young. And the remarkable thing is that some of those photons are passing through your body right now. They pass through walls, through windows, through air, through skin, through bone, through everything, leaving no trace, not interacting, simply continuing their journey. You are bathing in the light of the early universe without ever noticing it. But there is another aspect of the early universe even stranger than that. Some physicists believe that the rapid expansion in the first second called inflation may not have ended everywhere at the same time. In the universe, we observe, inflation ended after about 10 to the power of negative 32 seconds. The energy driving inflation transformed into matter and radiation, and the universe entered the slower, steadier expansion that continues today. But there may be other regions of space, very far away, beyond our observable horizon, where inflation never ended. Those regions may still be undergoing extremely rapid expansion, continuously creating new space at an astonishing rate. During that process, random quantum fluctuations, tiny variations in energy that occur naturally everywhere, according to quantum mechanics, may cause some regions within the inflationary field to stop expanding rapidly and shift into normal expansion. Each such region becomes its own bubble universe, similar to ours. Imagine a pot of boiling water. On the surface, bubbles of steam form as water evaporates. Each bubble separates from the liquid, rises, and eventually bursts. Meanwhile, new bubbles continually appear. Eternal inflation may behave in a similar way. A sea of perpetual inflation in which bubble universes continually form. Each bubble is a universe with its own Big Bang, its own history, and its own destiny. And even stranger, those bubble universes may have different physical laws. The physical constants we measure, such as the speed of light, the gravitational constant, and the mass of the electron, may take different values in other bubbles. The number of spatial dimensions may differ. The fundamental forces may be stronger or weaker. In some universes, gravity may be so strong that everything collapses into black holes immediately after formation. In others, electromagnetism may be so weak that atoms cannot exist. In most universes, conditions may be unsuitable for life as we know it. But in a few, a very small number, the physical constants fall within a narrow range that allows stars to form, planets to condense, complex chemistry to develop, and eventually life to arise. And we naturally exist in one of those rare universes. Not because we are special, or because there is any design or purpose, but simply because we can only exist in a universe whose conditions permit our existence. This idea is called the multiverse. It remains controversial in the scientific community because we have no way to observe other universes if they exist. Light from another bubble universe can never reach us, because the space between bubbles expands faster than the speed of light. The bubbles remain forever separated, never interacting or communicating. But some theoretical physicists argue that the multiverse is a natural consequence of inflation theory and may explain why the physical constants in our universe appear finely tuned for life. And among all those possibilities, we live in a universe where light was released 13.8 billion years ago, where stars formed, where life arose, and where you, at this very moment, are lying here listening to this story. The light from the early universe is a kind of imprint, a window into the distant past. But there are deeper and stranger imprints hidden within the very structure of space and time. These imprints may tell us the story of the first seconds, perhaps even what happened before the Big Bang, if a before existed. Most black holes we know form from the collapse of massive stars. When a star, with a mass at least 20 times that of the Sun, exhausts its nuclear fuel, gravity pulls all of its matter inward. The star's core is crushed under enormous pressure that overwhelms even the resistance of neutrons, and it collapses into a point of infinite density called a singularity, surrounded by an event horizon, the boundary beyond which nothing, not even light, can escape. That is a stellar black hole. But there is another kind of black hole that may have formed during the first seconds after the Big Bang, long before any star existed. These are called primordial black holes. During the extremely dense and hot era after the Big Bang, matter was not perfectly uniform. There were tiny fluctuations in density, regions slightly more concentrated than their surroundings. Most of these fluctuations were very small, only a few parts per million, not enough to create anything special in the early stages. But in some regions where the density fluctuation was large enough, the enormous pressure of the early universe may have compressed that region beyond its limits. The gravity from the concentrated matter may have overwhelmed opposing forces, causing that region to collapse directly into a black hole without ever forming a star. This could have happened in the first fraction of the first second, when the universe was still tiny and dense enough that such fluctuations could form black holes. These primordial black holes could have vastly different sizes. Some may be smaller than an atom, but have the mass of a mountain. Imagine the entire Mount Everest compressed to a size smaller than a proton. That is the density of a small primordial black hole. Some others may be larger, with masses equal to thousands, millions, or even billions of times the mass of the Sun. These black holes, if they exist, may have become the seeds of the supermassive black holes we see at the centers of most large galaxies today. But why are primordial black holes important for understanding the early universe? Because if they exist, they are living fossil stones from the very first era. The internal structure of a black hole, according to some theories, may preserve traces of the physical conditions at the moment it formed. When matter falls into a black hole, information about the state of that matter does not completely disappear. According to the holographic principle proposed by some physicists, the information may be encoded on the surface of the event horizon. This means that a primordial black hole may carry information about the temperature, density, and composition of the universe at the time it formed. If we could find and study a primordial black hole, we could learn things never known before about the first second of the universe and about extreme conditions that no experiment on Earth can reproduce. The problem is that we have not yet found a primordial black hole with certainty. Small black holes are very difficult to detect because they do not emit much light. We can detect them only through their gravitational effects or through Hawking radiation if they are small enough. Hawking radiation is a quantum phenomenon that Stephen Hawking predicted in 1974. According to this theory, black holes are not completely black. They can emit a very faint type of radiation due to quantum effects near the event horizon. Near the boundary of a black hole, virtual particle pairs are constantly created from empty space due to quantum fluctuations. A pair consisting of one particle and one antiparticle appears, and normally they would annihilate each other instantly. But if one of the two particles falls into the black hole while the other escapes, the black hole loses a small amount of energy, and the escaping particle can be detected as radiation. For large black holes, this radiation is extremely weak and nearly impossible to measure. But for small black holes, especially primordial black holes with masses smaller than a mountain, Hawking radiation may be strong enough to detect. And here is something interesting. The smallest black holes from the early universe, if they exist, may be in the final stage of evaporation right now. After 13.8 billion years of emitting Hawking radiation, they may be nearly out of mass and may explode in a brief flash of gamma light. Scientists are searching for these mysterious gamma bursts, hoping that some of them may be signs of dying primordial black holes. If we detect one, it will be direct evidence of the existence of black holes from the early universe. But traces from the earliest moments are not only in objects such as black holes. They are also in the very nature of time. We are familiar with the idea that time flows steadily and the same everywhere. 1 second here is the same as 1 second anywhere else. 1 hour is 1 hour, whether you are on Earth or on the moon or on a distant star. But Einstein's theory of relativity showed that this is not true. Time is not absolute. It can flow faster or slower, depending on two factors, which are velocity and gravity. If you move at very high speeds close to the speed of light, time for you will flow more slowly than for someone standing still. If you are near a massive object, such as a star or a black hole, where gravity is strong, time also flows more slowly. These effects have been verified by experiment. Atomic clocks on GPS satellites must be corrected for time dilation because they are farther from Earth where gravity is weaker, causing time to flow slightly faster. Without correction, GPS would accumulate errors of many kilometers each day. Now, think about the early universe. In the first seconds after the Big Bang, the universe was extremely dense. There was enormous energy density. And according to general relativity, high energy density corresponds to strongly curved space. When space is strongly curved, time is affected as well. Near the Big Bang, where the curvature of space-time approaches infinity, the concept of time becomes vague. Some quantum physicists believe that at the initial extreme moment, there was no clear distinction between space and time. They merged into a single entity called quantum space-time, where the usual laws of classical physics no longer applied. Stephen Hawking and James Hartle proposed a model called the no-boundary proposal. According to this model, if we could go close enough to the Big Bang, time gradually transforms into a spatial dimension. Imagine you are traveling north on the surface of Earth. As you approach the North Pole, the meridians converge. At the North Pole itself, the concept of north no longer has meaning. You cannot go farther north because you are already at the northernmost point. Similarly, as we go backward in time toward the Big Bang, time gradually converges and eventually becomes a spatial dimension. At the Big Bang, there is no separate time axis. There are only 4 spatial dimensions, and in such a space, the question, what happened before the Big Bang, becomes meaningless. Just like the question, what lies north of the North Pole? There is no before, because time does not exist there. These ideas are very difficult to grasp because they lie outside our everyday experience. We live in a world where time seems to flow steadily and unchanging. But reality may be far more complex and strange. Time, which feels so familiar and natural to us, is actually a physical quantity that can bend, stretch, and even disappear under extreme conditions. Now, let us return to the cosmic microwave background, the CMB that we mentioned earlier. When scientists measured the CMB using extremely sensitive satellite telescopes such as COBE, WMAP, and the more recent Planck, they did not see a perfectly uniform image. They saw tiny ripples and extremely small temperature fluctuations only a few parts in the 100,000 degrees, but they carry enormous significance. Imagine you take a picture of the CMB sky. If it were perfectly uniform, the entire picture would be the same color. But in reality, when you zoom in and apply a sensitive color scale to show the very small temperature differences, you will see a complex pattern of slightly hotter regions and slightly colder regions. These regions are not distributed randomly. They have a structure and a pattern that can be measured and analyzed. These ripples are traces of density fluctuations in the early universe. Regions with slightly higher density appear as slightly hotter areas in the CMB. Regions with lower density appear as slightly colder areas. And more importantly, these tiny fluctuations became the seeds for all the structure we see in the universe today. The higher density regions, over billions of years, attracted surrounding matter through gravity and grew into galaxies, galaxy clusters, and superclusters. The lower density regions became the voids and the vast empty spaces between large-scale structures. In other words, the ripples in the CMB are the blueprint for the structure of the entire present universe. They are the seeds of everything we see today, every galaxy, every star, every planet, even Earth and us. But what is the origin of these ripples? Why is the universe not completely uniform? Most scientists believe that they originated from quantum fluctuations during the inflation era, the first second after the Big Bang. In quantum mechanics, nothing is perfectly smooth or perfectly uniform at the microscopic scale. There are always tiny fluctuations, random variations in energy and density. Normally, these fluctuations are extremely small and exist for an extremely short amount of time. But during the inflation era, when the universe expanded at an enormous rate, microscopic quantum fluctuations were stretched into macroscopic structures. Imagine you draw a picture with very small details on a sheet of paper. Then you stretch that sheet by a trillion times. The tiny details suddenly become enormous structures that can be seen clearly from far away. Inflation did the same with quantum fluctuations. Tiny variations at the subatomic scale were stretched to the scale of galaxies and larger. And when scientists analyzed the pattern of the ripples in the CMB, they found exactly the type of distribution that inflation theory predicts. The fluctuations are random, but follow a characteristic statistical distribution. They are not too large, not too small, and they have a characteristic scale related to the size of the universe at the moment inflation ended. This is one of the strongest pieces of evidence for inflation. It not only explains why the universe is nearly flat and uniform on large scales, but also predicts exactly the type of small fluctuations that we observe. But there is an even stranger possibility. Some physicists believe that the ripples in the CMB may contain traces of events that happened before the Big Bang, if a before truly exists. If our universe is the result of a cycle of expansion and contraction, a big bounce instead of a simple Big Bang, then there may be signals from a previous universe, from a previous cycle. In the Big Bounce model, the universe does not begin from a singularity. Instead, it comes from the contraction of an earlier universe. When the old universe contracted to a maximum density, quantum effects may have prevented complete collapse and caused the universe to bounce back. beginning expansion once again. If this happened, some information from the earlier universe may have been transmitted through the contraction and rebound phase and encoded in the structure of the CMB we observe today. These signals would be extremely small and very difficult to detect, hidden within noise and other effects. But if we could find them, they would be evidence that the Big Bang was not an absolute beginning, but only a transition in a much longer history, possibly an infinite one. Scientists have searched for unusual signals in the CMB. They have found some strange features, such as a large, unusual cold spot or a slight asymmetry between the two hemispheres of the sky, but it is unclear whether these anomalies have deep physical meaning or are simply random statistical variations. More data, better analysis, and perhaps future generations of telescopes may be needed to answer these questions. But simply knowing that we can ask such questions, that we can search for traces of events that may have happened before the Big Bang in observational data, is a testament to the power of modern science. Consider this. We, living beings on a small planet, using technology we created ourselves, can observe light emitted 13.8 billion years ago, analyze it with precision down to millionths of a degree, and from it infer the conditions of the universe when it was only a few 100,000 years old. We can see tiny ripples from the earliest era and recognize that they are the seeds of all present structure. We can predict the existence of primordial black holes and search for them. We can consider the nature of time near the Big Bang and realize that it may not behave like the time we experience. And all of this is not abstract philosophy or wild speculation. It is science grounded in observation, experiment, mathematics, and careful reasoning. The universe is telling us its story through the traces it has left behind, and we are learning how to read those traces. Every photon from the CMB is a messenger from the past. Every small fluctuation in the CMB temperature is a word in the story of origin. Every primordial black hole, if we find one, will be a fossil stone from the earliest era. When you look up at the night sky on a clear night far from city lights, you may see thousands of shimmering stars. They are scattered across the sky, appearing to be distributed randomly with no obvious pattern. Some areas have more stars, like the faint, bright band of the Milky Way stretching across the sky. Other areas are sparse, with only a few lonely stars. But if you could zoom out and look at the universe from far beyond any human reach, you would see an entirely different picture. A picture of order and structure on an unimaginable scale. Let us begin with what we know. Stars do not exist alone or randomly in space. They gather into large systems called galaxies. Our Milky Way galaxy contains about 200 to 400 billion stars, all orbiting a common center, held together by gravity. But galaxies do not exist alone either. They gather into groups and clusters. The Milky Way belongs to a small group called the Local Group, which contains about 80 galaxies, including the Andromeda Galaxy, the nearest large galaxy to us, and dozens of smaller dwarf galaxies. And galaxy groups gather into larger clusters. The local group is part of the Virgo supercluster, a collection containing more than 100 galaxy groups and clusters spanning about 110 million light-years. But even the supercluster is not the final level of structure. In 2014, astronomers mapped the motion of nearby galaxies and discovered that the Virgo supercluster is actually just a small part of an even larger structure. They called it Laniakea, a Hawaiian word meaning vast, immeasurable heaven. Laniakea contains about 100,000 galaxies and spans 520 million light-years. All the galaxies in Laniakea are moving toward a common gravitational attractor, pulled by the combined mass of this enormous structure. We live inside Laniakea. Earth, the solar system, the Milky Way, all are tiny specks within a structure stretching hundreds of millions of light-years. But Laniakea is not the largest structure. Farther away, astronomers have discovered even more gigantic structures. One of the largest structures ever found is the Boss Great Wall, discovered in 2016 through the Baryon Oscillation Spectroscopic Survey. It is a wall of galaxies and dark matter, stretching about 1 billion light-years from end to end. Take a moment to reflect on this number. 1 billion light-years. Light travels at 300,000 kilometers per second. In 1 year, it travels about 9.5 trillion kilometers. And the Boss Great Wall is 1 billion times that distance. If you could travel at the speed of light, the fastest speed possible in the universe according to relativity, and you started at one end of the Boss Great Wall, you would need 1 billion years to reach the other end. During that time, if you looked out the window of your spacecraft, you would continually see galaxy after galaxy passing by, trillions of galaxies for an entire billion years. For comparison, the entire observable universe has a diameter of about 93 billion light-years. The Boss Great Wall accounts for more than 1% of that length. It is one of the largest structures we know. But the Boss Great Wall does not stand alone. Many similar structures have been discovered, such as the Sloan Great Wall, the Hercules Corona Borealis Great Wall, and others. Each one is an enormous collection of thousands or millions of galaxies arranged into long strands, flat sheets, and filaments stretching across space. When scientists map the positions of millions of galaxies observed from large sky surveys, they discovered something remarkable. Galaxies are not distributed randomly. They form a complex network, a structure with characteristic shapes that repeat on many different scales. This is called the cosmic web. Imagine a giant net stretched across space, but not a flat net. It is a three-dimensional net, intricate and detailed. The strands of the net are made of thousands of galaxies lined up in long, thin filaments. These filaments are not straight, but curve and twist into complex shapes. At the points where many filaments meet, where multiple galaxy strands intersect, lie the superclusters. These are the regions with the highest galaxy density, where thousands of galaxy clusters gather, each cluster containing hundreds or thousands of galaxies. Between the filaments, between the galaxy strands, lie enormous empty spaces. These regions are called supervoids. They are nearly empty regions of space with very few or no galaxies. Some supervoids have diameters of hundreds of millions of light years. If you stood in the middle of a supervoid and looked in all directions, you would see almost complete darkness. The nearest galaxy might be hundreds of millions of light years away. There would be no bright stars nearby, no Milky Way, only a few faint points in the distance, and the rest would be darkness. One of the largest known supervoids is the Boötes Void, also called the Great Void, with a diameter of about 330 million light-years. When it was first discovered in 1981, astronomers were astonished. They did not expect such large empty regions to exist in the universe. Inside the Boötes Void, only about 60 galaxies are known, while a region of the same size elsewhere might contain thousands of galaxies. The matter density in the supervoid is about 90% lower than the average density of the universe. But even these empty regions are not completely empty. They still contain thin gases, mainly hydrogen and helium. They contain dark matter, the invisible substance that makes up most of the mass of the universe. And they contain dark energy, the mysterious force driving the accelerated expansion of the universe. The difference is that their density is far lower than in other regions. This cosmic web structure did not form randomly. It is the inevitable result of billions of years of evolution under gravity, starting from tiny fluctuations in the early universe. Remember the tiny ripples in the CMB that we discussed earlier. Those extremely small density fluctuations, only a few parts in 100,000, were the seeds of all structure. In regions with slightly higher density, even by only 0.001%, gravity was slightly stronger. Matter around those regions was pulled inward. As matter accumulated, mass increased. Gravity became stronger, and even more matter was pulled in. This process reinforced itself. Rich regions became richer, and poor regions became poorer. Over billions of years, the initial tiny fluctuations were amplified millions of times. The highest density regions became superclusters. The medium density regions became filaments. The lowest density regions became supervoids because matter in those regions was drawn outward toward denser areas. The result is the web-like structure we see today. Dense galaxy filaments surrounding large empty voids with superclusters at the nodes. And interestingly, this structure resembles something else that we are familiar with, the neural network in the brain. When scientists compared images of the cosmic web with images of neurons in the human brain under a microscope, they discovered striking similarities. In the brain, neurons connect to each other through long fibers called axons. Many neurons cluster at nodes, forming processing centers. Between the centers lie relatively empty gaps, and the whole system forms a complex hierarchical network. The cosmic web has a similar structure. Galaxies cluster into filaments. Multiple filaments meet at superclusters. Between the filaments lie supervoids, and the whole system forms a complex network. Of course, the physical mechanisms behind the two networks are completely different. The brain is shaped by biological processes and evolution. The universe is shaped by gravity and the dynamics of dark matter. The scale difference is also enormous. But the similarity in form suggests that there may be deeper mathematical principles governing how complex systems self-organize, regardless of what they are or at what scale they exist. It is possible that complex networks, from brain neurons to cosmic galaxies, from social networks to the internet, all follow certain shared mathematical rules for how nodes connect efficiently. Scientists call this the study of network theory. And they have found that many natural and artificial networks share common features, such as having a few highly connected central nodes, while most nodes have fewer connections. But is this only a coincidence? Or does it hint at something deeper about the relationship between mind and universe, between consciousness and the structure of reality? We do not yet know the answer. But this similarity inspires many to reflect on our place in the universe and the nature of existence. Now think about our position in this enormous structure. Earth orbits the Sun. The Sun lies in the Milky Way, about 26,000 light-years from the galactic center, orbiting that center at about 220 kilometers per second, completing one revolution in roughly 225 million years. The Milky Way belongs to the local group, a small cluster of about 80 galaxies spread across roughly 10 million light-years. The local group is part of the Virgo supercluster, containing more than 100 galaxy clusters spread across 110 million light-years. The Virgo supercluster lies within Laniakea, a superstructure containing 100,000 galaxies spanning 520 million light-years. Laniakea is only one of countless similar structures within the observable universe. We are part of a tiny filament in the cosmic web, a filament that runs between supervoids. And this entire structure is moving, growing, and evolving over time. Galaxies within the same filament are slowly moving closer together due to gravity. Filaments are gradually becoming denser. The supervoids are expanding, becoming emptier as matter continues to be drawn out of them. And all of this takes place against the backdrop of cosmic expansion. The space between the largest structures is increasing. Distant galaxies are receding from us at ever greater speeds because of dark energy. In the very distant future, trillions of years from now, the cosmic web may look very different. Filaments could dissolve as the galaxies within them are pulled apart by the expansion of space. Or conversely, in some regions, matter might clump more tightly, forming new superstructures. But one thing is certain: the structure of the universe is not static. It is dynamic. It lives. It constantly changes, although at such a slow pace that from the viewpoint of a human lifetime, it appears immutable. When you look up at the night sky and see the twinkling stars, remember that each of those stars is part of a galaxy. Each galaxy is part of a filament. Each filament is part of the cosmic web. And the cosmic web stretches across the entire observable cosmos, from this horizon to the opposite horizon. We live in one of the filaments of that network, a tiny filament in a structure so vast that the mind struggles to grasp it. But do not feel small because of that. From atoms to stars, from stars to galaxies, from galaxies to filaments, from filaments to the cosmic web. Everything is connected. Everything is one. You breathe in time with the universe. You move with the Earth around the Sun, with the Sun around the galactic center, with the galaxy in the flow of Laniakea, and with Laniakea within the vast cosmic web. There is a special type of particle you may never have heard of, yet trillions upon trillions of them are passing through your body right now as you lie here listening to this story. They are called neutrinos. Neutrinos are extraordinarily tiny particles with masses nearly zero, millions of times smaller than an electron. They carry no electric charge, have no color, emit no light, and interact only very weakly with matter. They are like ghosts, passing through everything as if nothing resists them. A neutrino can travel through the entire Earth from one pole to the other without colliding with a single atom. Most other particles, when they encounter solid matter, will be absorbed or scattered within micrometers, but not neutrinos. For neutrinos, Earth is almost as transparent as air, and in many ways, even more transparent. Each second, about 65 billion neutrinos from the Sun pass through every square centimeter on Earth. That means that while you read this, thousands of billions of solar neutrinos have passed through your body from head to toe, from left to right, from front to back. They pass through skin, flesh, and bone, through every cell without leaving a trace. You do not feel them. They do not interact with DNA. They do not cause mutations. They do not generate heat. They do nothing. They simply pass through like invisible breezes across a mesh. Neutrinos are produced in many different processes. They are born in the Sun's core when hydrogen atoms fuse into helium in nuclear reactions. They are created when a massive star explodes as a supernova, releasing a tremendous burst of neutrinos into space for a few seconds. They are produced when high-energy cosmic rays strike Earth's atmosphere and generate showers of secondary particles. And they are produced in nuclear reactors, both natural reactors deep in the Earth and artificial ones in power plants. But there is an even more ancient and distant source of neutrinos that we have never directly detected, the neutrinos from the first second of the universe. Just as the cosmic microwave background is the fossil light from the early universe, physicists believe there must be a cosmic neutrino background, the CNB. These neutrinos were created only 1 second after the Big Bang, when the universe was still so hot that particles collided with enormous energies, enough for weak nuclear processes to produce neutrinos. At that time, the universe's temperature was about 10 billion degrees Kelvin, hotter than the core of any star today. As the universe expanded and cooled, the reactions that made neutrinos ceased, and the neutrinos that had been created began to stream freely, just as photons in the CMB were released after 380,000 years. But neutrinos were freed much earlier, after only 1 second, because they interact more weakly than photons. While photons remain trapped in the plasma until atoms formed, neutrinos were able to roam almost immediately. From that time until now, over 13.8 billion years, those neutrinos have quietly traversed the cosmos, unimpeded and non-interacting, traveling in straight lines at speeds close to that of light. It is estimated that there are about 330 CNB neutrinos in each cubic centimeter of space. That means that in the room where you lie now, There are billions upon billions of neutrinos from the first second of the universe. And each second, thousands of billions of those neutrinos pass through your body from head to toe. But because they interact so weakly, we cannot sense them. They leave no trace on skin, bone, or brain. They simply pass through, silently like ghosts from a distant past. And sadly, we have not yet directly detected the CNB. We know it must exist from theory and from calculations about the early universe. But CNB neutrinos have energies so low and interaction probabilities so tiny that they are nearly impossible to detect with current technology. To give a sense of the difficulty, to detect solar neutrinos, scientists had to build massive detectors containing thousands of tons of water or special liquids and place them deep underground to shield from cosmic ray noise. Even with such detectors, they observe only a few dozen events per day out of the billions upon billions of neutrinos that pass through. CNB neutrinos have energies millions of times lower than solar neutrinos, making them almost impossible to capture. But scientists do not give up. They are developing new techniques and more sensitive detectors in the hope that one day we will directly detect the messengers from the universe's first second. If we succeed, it will open a window onto the universe when it was only 1 second old, earlier than the CMB, closer to the Big Bang than any other direct observation. But neutrinos are not the only ghosts in the universe. There is something else, much more mysterious, that we know must exist, but do not yet know what it is. Dark matter. We will discuss dark matter in detail later, but for now, just know that there is a form of matter that emits no light, absorbs no light, and reflects no light. It is completely invisible to every form of electromagnetic radiation. We know it exists only because of its gravitational effects on stars and galaxies. Dark matter makes up about 27% of the universe's total energy density. Ordinary matter, the kind that makes stars, planets, and us, accounts for only about 5%. That means that in this room, in the air you breathe, in the space around you, there is 5 times more dark matter than ordinary matter. Yet you cannot see it, touch it, or sense it by any of your senses. If dark matter consists of particles, as the most popular hypotheses suggest, then those particles are also passing through you every second, like neutrinos. They may be passing through the walls, through the bed you lie on, through your body, leaving no trace. You are bathing in a sea of invisible particles from the cosmos. Solar neutrinos. Neutrinos from the first second. Possibly dark matter particles. All silently passing through you, without pause, in every moment of your life. Beyond neutrinos and dark matter, there are other ghosts lurking in the very fabric of empty space. Einstein, in general relativity and later work, showed that empty space is not truly empty or perfectly still. Even if you remove all matter, all radiation, all observable stuff, something remains. Vacuum energy. According to quantum mechanics, empty space always experiences tiny energy fluctuations. Even in absolute vacuum, where no particle exists, quantum fields still fluctuate, varying and producing pairs of virtual particles that pop into and out of existence in extremely brief instants. A pair of virtual particles, for example, an electron and a positron, can appear from nothing, exist for a time shorter than 10 to the negative 21st seconds, then annihilate and disappear. This time is far too short for direct measurement, but long enough to have real physical effects. These fluctuations, these virtual particle pairs, create a background energy, a small but non-zero pressure, even in perfectly empty space. We know vacuum energy truly exists because it has been measured in the laboratory through the Casimir effect. When two metal plates are placed extremely close to each other in a vacuum, they are pushed together by a tiny force. This force arises from the difference in quantum fluctuations between the narrow gap between the plates and the space outside them. So, vacuum energy is real. But there is a major problem. When physicists calculate vacuum energy based on quantum mechanics, they obtain an extremely large number. If they sum all the fluctuations from all possible quantum fields, the vacuum energy should be so enormous that the universe would be torn apart immediately. But reality is not like that. The universe is still here. And when astronomers measure the actual vacuum energy via observations of cosmic expansion, they find a very small number, smaller than the theoretical quantum estimate by 120 orders of magnitude. This is called the cosmological constant problem, or the vacuum energy problem. And it is one of the greatest mysteries, perhaps the greatest, in modern physics. Why do theory and observation differ so horrendously? Why is the actual vacuum energy so small when theory predicts it should be enormous? We do not know the answer. But interestingly, vacuum energy, even if tiny, might be the origin of dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy makes up 68% of the universe's total energy budget, and we do not know what it is. One possibility is that it is vacuum energy, the intrinsic energy of empty space. If that is the case, it means most of the universe is made of the energy of space itself, arising from tiny quantum fluctuations happening everywhere at every moment. Even if you think you are in an empty room with nothing around you, in fact, you are surrounded by a sea of fluctuating quantum energy. Virtual particles appear and vanish. Quantum fields oscillate. All of this creates a tiny pressure that is driving the universe to expand faster. This is one of the strangest ideas of modern physics. Nothing is really nothing. Even perfectly empty space is teeming with activity at the quantum level. And there is another kind of particle coming from space that we can observe more easily, although it is still mysterious. Cosmic rays. Cosmic rays are not rays in the sense of light. They are particles of matter, mostly protons, but also some heavier atomic nuclei and even electrons, moving at extremely high speeds close to the speed of light. They come from space, from beyond the solar system, and even from outside our galaxy. Some originate from stars exploding as supernovae. Others may come from supermassive black holes at the centers of distant galaxies. And a very small fraction, the ultra-high energy cosmic rays, have sources we still do not know. When a high-energy cosmic ray collides with Earth's atmosphere, it strikes an atom of air, typically nitrogen or oxygen. That collision produces a shower of secondary particles, pions, muons, neutrinos, and many others. Those particles collide in turn and produce yet more particles. The result is a cascade spreading out like a cone, with millions of particles raining down across a large area on the ground. Some of these particles, especially muons, can penetrate many meters of soil or rock before being absorbed. And some of these particles can pass through your body. Each minute, about 1 muon from cosmic rays passes through the body of an average person. If that muon traverses a cell and collides with DNA, it can cause a mutation. Most such mutations are harmless or repaired by the cell's repair mechanisms, but occasionally a mutation may persist. Over millions of years, random mutations from cosmic rays and other sources have been part of the engine of evolution, generating genetic diversity on which natural selection can act. In other words, cosmic rays from space have contributed to the evolution of life on Earth. Particles from distant stars and from violent explosions at the edges of galaxies have influenced the DNA of our ancestors and helped shape us into what we are today. And some cosmic rays carry extraordinarily high energies. These are called ultra-high energy cosmic rays. A single one of these particles can carry energy comparable to that of a tennis ball thrown at 100 kilometers per hour. Think about that for a moment. A tennis ball contains billions upon billions of atoms. Yet here we are, talking about a single particle, a proton, carrying the energy equivalent of the whole tennis ball in motion. That energy is so enormous that we do not know what natural process could accelerate a particle to that level. There is no star or supernova that we know of that can accelerate a particle to such energies. Some hypotheses suggest they originate from supermassive black holes that shred and accelerate matter in their accretion disks. Others propose they come from violent collisions between galaxies, where gigantic shock waves could accelerate particles. Some even speculate that a fraction might arise from the decay of heavy particles left over from the early universe. But the precise origin remains a mystery. That is one of the big questions physicists are trying to answer by building gigantic detectors spread over thousands of square kilometers to catch these rare events. The observable universe, with all its galaxies, galaxy clusters, and enormous structures, is only part of the whole cosmos. And this is not philosophical speculation, but a direct consequence of physics. Light travels at a finite speed, 300,000 kilometers per second, and the universe has existed for a finite time, about 13.8 billion years. That means we can see only those regions of the universe from which light has had enough time to reach us. This boundary is called the observable universe horizon. Because of cosmic expansion, this horizon lies about 46 billion light-years away in every direction, forming a sphere with us at the center. But beyond that horizon, the universe continues. It may extend infinitely, or it may end somewhere. We do not know, because we cannot see it. Yet there are hints that what lies beyond our observable horizon might influence what we observe inside it. One of the strangest phenomena is called dark flow. In the early 2000s, astronomers were studying the motions of hundreds of galaxy clusters by observing how the cosmic microwave background is distorted when it passes through those clusters. They expected to see clusters moving in different, roughly random directions, reflecting the local gravitational influences of nearby structures. But instead, they found a surprise. Galaxy clusters in a large region of the sky appear to be moving in roughly the same direction, with speeds around 600 to 1,000 kilometers per second. Here is a collective motion, a shared flow, as if something invisible is pulling thousands of galaxy clusters toward a point far beyond our observable horizon. According to standard cosmology, the expansion of the universe should cause galaxies to move away from each other in all directions uniformly on large scales. There should not be a common flow in one particular direction that stretches across billions of light years, but observations show that there is. The hypothesis is that something extremely large and extremely massive lies beyond our observable horizon, and its gravity is pulling galaxy clusters toward it, even from such enormous distances. It may be a superstructure, a mass concentration, larger than anything we have ever seen in the observable universe. Or it may be the imprint of another universe, another cosmic bubble in the multiverse, interacting with ours through gravity despite being separated by unimaginable distances. Of course, the discovery of dark flow remains controversial in the scientific community. Some recent studies using better data from the Planck satellite suggest that the effect may not truly exist or may be much smaller than first reported. It may simply be the result of analysis errors or interference from other sources. But even if dark flow is eventually proven not to exist, the idea that something beyond our vision can influence what we see remains compelling and worth contemplating. It reminds us that the observable universe may be only a tiny part of a much larger entity. And there is something else, closer to us, within the observable universe, but no less mysterious: the Great Attractor. This is a region of space located about 150 to 250 million light-years away in the direction of the constellations Centaurus and Triangulum Australe in the southern hemisphere. This region has an estimated mass equal to about 10,000 to 100,000 times the mass of the Milky Way, and it is pulling us toward it. The Milky Way, along with all the galaxies in the local group, in the Virgo supercluster, and even the entire Laniakea structure, is moving toward the Great Attractor at a speed of about 600 kilometers per second. To visualize this speed, each second we move 600 kilometers closer to the Great Attractor. In 1 hour, the distance shrinks by more than 2 million kilometers. In 1 year, it shrinks by more than 18 billion kilometers, and this process has been happening for billions of years. But the problem is that we cannot see the Great Attractor directly. It lies behind the plane of the Milky Way. Thick gas and dust in our galactic disk block our view, creating a zone of avoidance where we cannot observe what lies behind it using visible or near-infrared light. We know the Great Attractor is there only because we see its gravitational influence on surrounding galaxies. By measuring the velocities of thousands of galaxies in the region and analyzing their motion patterns, astronomers can infer that a massive concentration must be there pulling everything toward it. And as they study it further, the picture becomes more complex. Astronomers later discovered that the Great Attractor is only part of a much larger structure called the Shapley supercluster. which lies even farther away, about 650 million light-years from us. The Shapley supercluster is one of the largest mass concentrations known in the nearby universe, containing more than 8,000 galaxies packed into a relatively small region of space. Its total mass may reach tens of thousands of times the mass of the Milky Way. And it is also pulling us, along with the Great Attractor and countless other galaxies in the region, toward it through its enormous gravitational pull. So how are we moving through space? Earth orbits the Sun at about 30 kilometers per second. The Sun, along with the entire solar system, orbits the center of the Milky Way at about 220 kilometers per second. The Milky Way is moving toward the Andromeda Galaxy at about 110 kilometers per second. Both galaxies are falling into the local group. The local group is falling into the Virgo supercluster, and everything is being pulled toward the Great Attractor and the Shapley supercluster. When you add all these motions together, the result is a complex, curved, spiraling trajectory through four-dimensional space. We are not merely orbiting. We are in free fall within the gravitational fields of enormous structures, pulled by invisible forces from masses that in some cases we cannot even see. All of this shows that the universe is not a quiet or static place. It is a place full of motion and flow. Galaxies are not standing still. They move under the influence of gravity from massive structures, some visible and some beyond our sight, but still affecting us. And it is possible that the region we call the observable universe is only a tiny part of a much larger whole, a cosmos we may never fully see, but that still influences us through gravity. Imagine standing in the middle of a vast ocean on a moonless night with no light except what you carry. You have a small flashlight. The light from the flashlight illuminates only a small patch of water around you, perhaps only a few meters. Beyond that illuminated patch lies complete darkness. You know the ocean stretches far beyond. You can feel currents pushing you in certain directions. You can feel waves striking your body from distant places. You know there is something much larger out there, but you cannot see it. Our observable universe is similar. We have a region of light where we can see galaxies and structures, but beyond that lies darkness and the unknown. And yet we still feel the influence of whatever lies in that darkness through the motion of galaxies and through enormous flows pulling us toward an unclear destination. Perhaps someday, with better technology and more precise observations, we will understand these forces and the invisible masses pulling us. Or perhaps some mysteries will remain forever out of reach, hidden in regions of space where light has never had time to reach us. But simply knowing that there are things out there larger than what we see is enough to expand our minds and help us recognize our small but special place in the vast universe. Among all the fundamental forces of nature, gravity is the one we are most familiar with in daily life. It keeps us on the ground. It keeps the moon orbiting Earth. It keeps the planets in the solar system. It keeps stars within galaxies. It is the force that shapes the structure of the entire universe on large scales. But when physicists compare gravity with the three other fundamental forces, which are electromagnetism, the strong force, and the weak force, they discover something strange. Gravity is incomprehensibly weaker than the others. To understand how weak it is, imagine a small magnet. When you use it to pick up a paper clip, that tiny magnet is overcoming the gravity of the entire Earth. The electromagnetic force from a small magnet is stronger than the gravitational force from a planet with a mass of 6,000 trillion tons. If you calculate the exact ratio, gravity is weaker than electromagnetism by about 10 to the power of 36. That is a number with 36 zeros. It is weaker by 1,000 trillion times. Why is that? Why is gravity so much weaker than the other forces? This question is known as the hierarchy problem in physics, and it is one of the biggest mysteries that scientists are trying to solve. One of the most interesting ideas, proposed in the late 1990s, is that gravity might be leaking into hidden spatial dimensions that we cannot see or directly sense. Think about that for a moment. We live in a three-dimensional space. Up and down, left and right, forward and backward. Three directions. Time is the fourth dimension. But some modern theories, especially string theory, suggest that space may have more dimensions than what we experience. According to string theory, space may have 10 or even 11 dimensions. But the extra dimensions are curled up at an incredibly tiny scale, much smaller than a proton, so we cannot detect them. Imagine a rope. From far away, it looks like a one-dimensional line, but up close, it has thickness. It really has three dimensions, but two of them are so small that we do not notice them from a distance. Our universe might be like that. The three dimensions we see could be huge and unbounded, while the extra dimensions are curled up at the Planck scale, only about 10 to the power of minus 33 centimeters. The idea is that gravity may spread out into those extra dimensions, while the other forces stay confined to the three large ones. If that is the case, gravity seems weak to us because part of it is leaking into the hidden dimensions. It is like shouting inside a room with the window open. The sound is loud, but some of it escapes outside, so the room becomes quieter. If this idea is correct, then at extremely small scales, close to the size of those hidden dimensions, gravity might be much stronger than we expect. Experiments at particle accelerators such as the Large Hadron Collider could test this. So far, scientists have not found evidence for extra dimensions, but the search continues, and the idea of hidden dimensions is still possible. Now let us talk about the shape of space on very large scales. If you could zoom all the way out and see the entire observable universe as one object, what would it look like? Would it be flat like a sheet of paper, curved like the surface of a sphere, or shaped like a saddle? Cosmologists answered this question by measuring the curvature of space, using many methods including detailed maps of the small ripples in the cosmic microwave background. The result is that space is almost perfectly flat, at least within the part we can observe. If there is any curvature, it is extremely tiny. With our current instruments, space appears flat, but almost flat does not mean exactly flat. Space could have a slight curvature that is too small for us to measure today. If the universe is far bigger than the observable region, that curvature might show up on scales we cannot see. Just like Earth looks flat, when you stand on it, even though it is round. If space has positive curvature, like the surface of a sphere, the universe would be finite. If you traveled straight long enough, you would eventually return to where you started. But it would still have no edge, just like a sphere has no edge. If space has negative curvature, like a saddle, the universe would be infinite, and two parallel lines would slowly drift farther apart. If space is exactly flat, the universe would also be infinite, and simple Euclidean geometry would be correct everywhere. Right now, observations tell us that we are in the third case, or something very close to it. Space seems flat, or nearly flat. But why is that? This is not obvious. There are countless possible curvature values, yet our universe is incredibly close to zero. Inflation may be the reason. The rapid expansion in the first moment after the Big Bang stretched space so much that any curvature it had would be smoothed out, like blowing up a balloon until its surface looks flat from close up. Now let us talk about another strange idea allowed by general relativity: wormholes. A wormhole is a tunnel linking 2 points in space. It lets you travel between them without crossing the space in between. Think of a sheet of paper. 2 corners are far apart if you move along the surface. But if you fold the paper and punch a hole through, you can go from one corner to the other quickly. A wormhole works the same way, but in 3-dimensional space, or in 4-dimensional space-time. The math of general relativity says that wormholes can exist. Einstein's equations allow shapes of space that form tunnels like that. But there is a big problem. Most wormholes in the equations are extremely unstable. They collapse instantly, closing before anything, even light, can pass through. To keep a wormhole open, you would need something called negative energy matter, which has negative energy density and creates a repulsive gravitational effect. This kind of matter has never been seen in nature, although some tiny quantum effects may create small pockets of negative energy on microscopic scales. If negative energy matter exists in large enough quantities, then in theory, a wormhole could be built and kept open. You could step into one end on Earth and come out near a star thousands of light years away without traveling through the empty space between them. Even stranger, some wormhole solutions allow travel backward in time. If one end of a wormhole is moved at a speed close to the speed of light while the other end stays still, time dilation will make time flow at different rates at the 2 ends. And if you go through the wormhole in one direction, you might come out in the past compared to when you started. Of course, this leads to famous paradoxes such as the grandfather paradox. If you go back in time and stop your grandparents from meeting, you would never be born. So how could you go back in time in the first place? Most physicists believe that there must be some natural rule we have not discovered yet that prevents such paradoxes. Maybe by making time travel wormholes impossible to exist, or by ensuring that any attempt to change the past will automatically fail in some way. But we are not sure. And the idea that the universe might allow shortcuts through space, or even through time, is still a very appealing thought in theoretical physics. And there is an idea even stranger about the nature of space: the holographic principle. According to this idea, The three-dimensional universe we experience might only be a projection created from information encoded on a two-dimensional surface. Think of a hologram. When you shine light on a hologram correctly, a three-dimensional image appears, with depth and perspective. But all the information that creates the three-dimensional image is stored on the flat two-dimensional surface. The holographic principle suggests that our entire three-dimensional universe might be similar. All information about everything in our universe, every particle, every field, every event, could be written on a two-dimensional boundary of the universe. And what we feel as a three-dimensional world might only be a projection of that two-dimensional information, just like a hologram's three-dimensional image. This idea sounds wild, but it comes from serious research on black holes. When physicists studied how information is stored in a black hole, they discovered that the maximum amount of information inside a region seems to depend on the area of its boundary, not its volume. In other words, information in the universe seems to behave like information in a hologram, stored on the surface rather than the volume. If the holographic principle is correct, it would deeply change how we understand reality. It would mean that the three-dimensional space we move through, which feels solid and real, might only be our interpretation of data stored in a lower dimensional surface. Just as the three-dimensional image in a hologram is not truly three-dimensional, but is still a real and measurable phenomenon, our universe would still be real to us because we ourselves are part of the hologram. These ideas, hidden dimensions, wormholes, flat space that may curve at larger scales, the universe as a hologram, all come from the mathematics of modern physics. They are not science fiction, but possible consequences of theories built to explain reality. And it is amazing that we can even think about questions like this. Questions about the deepest nature of space and time, and try to test some of these ideas through experiments. The universe is far stranger than what we see with our eyes. Space may have more than three dimensions. Gravity may be leaking into hidden dimensions. Wormholes might exist even if we cannot use them. And our three-dimensional reality might be a holographic projection from two-dimensional data. These possibilities make the universe richer, deeper, and more mysterious. They remind us that what feels obvious and natural to us, such as three-dimensional space, one-dimensional time, or gravity pulling everything, may only be a part of a much bigger picture we have barely begun to understand. After electrons were captured by atoms and light was released, the universe entered a period called the Dark Ages. This was not darkness in the usual sense, but a phase with no new sources of light. The CMB had become too faint to see. No stars had formed yet. The universe was filled with neutral gas, mainly hydrogen and helium, floating quietly in the dark. But in that darkness, the seeds of change were growing silently. The tiny density fluctuations from the early universe, the same ripples we discussed in the CMB, began to grow under the pull of gravity. Regions that were slightly denser than average pulled in nearby gas. As the gas accumulated, the density increased. The gravitational pull strengthened, and more gas fell inward. This process continued slowly for tens of millions of years. clouds of hydrogen and helium gradually collapsed under their own weight. In the densest regions, pressure and temperature started to rise. As a gas cloud collapses, gravitational energy turns into heat. The cloud warms up. At first, the heat escapes as infrared radiation, which cools the cloud and lets it continue to collapse. But when the density becomes high enough, the heat can no longer escape efficiently. The temperature in the core begins to climb rapidly. Then, at a remarkable moment, around 100 to 200 million years after the Big Bang, the temperature in the core of a collapsing cloud reached about 10 million Kelvin, hot enough for nuclear fusion to begin. Hydrogen nuclei, simple protons, collided with enough energy to overcome their electrical repulsion and fuse together. 4 protons combined through a series of steps to form a helium nucleus, releasing energy as photons and neutrinos. With that reaction, the first star lit up. Light from the first stars pierced the darkness, illuminating the hydrogen around them, ionizing atoms and creating glowing bubbles of plasma. The Dark Ages ended. The era of ionization began. But the first stars did not resemble any star we see today. They were called population 3 stars. They were made entirely of primordial hydrogen and helium, with no heavy elements, such as carbon, oxygen, or iron, because these elements had not been created yet. Because of this pristine chemical makeup, population 3 stars were extremely massive. Their masses could be tens or even hundreds of times the mass of the Sun. Some may have reached 200 or 300 solar masses. The more massive the star, the hotter, brighter, and shorter its life. The Sun will live about 10 billion years. A star 100 times heavier might live only a few million years or even a few 100,000 years. Population 3 stars burned their hydrogen fuel at an incredible rate. They shone with tremendous intensity. A single star could outshine millions of suns. Their surface temperatures could reach 100,000 Kelvin or more compared to about 5,800 for the Sun. The light from these stars was mostly intense ultraviolet radiation. It illuminated the clouds of gas around them, ionizing the hydrogen and creating huge glowing regions visible from far away. But their short lives meant they did not last long. After burning through the hydrogen in their cores, they began fusing helium, producing carbon and oxygen. Then they fused carbon, forming neon and magnesium. Then oxygen, forming silicon and sulfur. Each stage happened faster than the one before because heavier fuels burn at higher temperatures and release less energy. Eventually, the core of the star became iron, and iron is the end of the line. Nuclear fusion that combines light nuclei into heavier ones releases energy, but iron is the most stable element. Fusing iron with anything else does not release energy. It consumes energy. So when the core becomes iron, the star's power source runs out. The pressure from nuclear fusion, which had been pushing outward and holding the star up against gravity, suddenly disappears. In a single moment, within just a few seconds, the entire iron core collapses. Electrons are forced into protons, forming neutrons. The core is crushed down to a size of only a few tens of kilometers, with unimaginable density. A single teaspoon of this material would weigh as much as a mountain. This collapse creates a massive shock wave that rushes outward from the core. The shock wave tears through the outer layers of the star and blasts them into space at tens of thousands of kilometers per second. The star explodes as a supernova. For several weeks, a supernova can shine brighter than an entire galaxy of billions of stars. The energy released in this explosion exceeds the total energy the star emitted over its entire lifetime. More importantly, in the extreme temperatures and pressures of a supernova, nuclear reactions continue, creating elements heavier than iron. Gold, silver, platinum, uranium, all the heavy elements are forged in the final seconds of a dying massive star. The explosion sends these elements into space. Carbon and oxygen from helium fusion. Silicon and sulfur from oxygen fusion. Iron from the core, and gold, silver, uranium from the supernova itself. These elements mix with the surrounding hydrogen and helium in space. When the next generation of stars forms from these enriched clouds, they contain not only hydrogen and helium, but also heavier elements. Each generation enriches the surrounding space with heavy elements. The first generation, population 3, had only hydrogen and helium. The second generation, population 2, had a small amount of heavy elements. The third generation, population 1, which includes our Sun, contains a much higher fraction of heavy elements, about 2% of its mass. And these heavy elements are the foundation for everything we know. Without carbon, there are no complex organic molecules. Without oxygen, there is no water. Without silicon, no rock. Without iron, no metallic planetary cores. Every atom in your body, except hydrogen, was created inside stars. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, the iron in your blood, all came from stars that lived and died billions of years before the sun was born. You are literally made of stardust. That is not a poetic metaphor, but a precise scientific truth. But stars do more than create heavy elements. Some of them, the most massive ones, leave behind something else: black holes. When a star, extremely massive, maybe more than 25 to 30 times the mass of the sun, collapses, its core does not stop at becoming a neutron star. It continues collapsing until it becomes a black hole, a region of space where gravity is so strong that nothing, not even light, can escape. These black holes, with masses from a few tens to a few hundreds of solar masses, are called stellar mass black holes. And they may be the seeds of something far larger, supermassive black holes. At the center of most large galaxies, including the Milky Way, there is a supermassive black hole with a mass of millions or even billions of suns. The black hole at the center of the Milky Way, Sagittarius A star, has a mass of about 4 million suns. The black hole at the center of galaxy M87, which was imaged for the first time in 2019, has a mass of about 6.5 billion suns. How such enormous black holes formed is still a major question. One possibility is that they began as stellar mass black holes created by the first stars. These small black holes could pull in gas, grow over time, and merge with each other as stars collided. Over billions of years, they would slowly build up to the giants we see today. Another possibility is that some supermassive black holes formed directly from the collapse of huge gas clouds in the early universe without passing through a star stage. If a gas cloud was large enough and dense enough and collapsed fast enough, it might skip star formation entirely and collapse straight into a black hole with thousands or millions of solar masses right from the start. We still are not sure. But observations show that supermassive black holes existed very early in the universe, only a few 100 million years after the Big Bang, suggesting they must have grown extremely fast or started out large. These supermassive black holes play a crucial role in the formation and evolution of galaxies. Galaxies do not appear fully formed. They grow over time through a process called hierarchical merging. Small gas clouds collapse and form small groups of stars, maybe only a few million. These small groups are pulled together by gravity, especially the gravity of the dark matter surrounding them, which we cannot see but which contains most of the mass. When two small stellar groups collide, they do not crash like rocks. The distances between stars are enormous compared to their sizes, so most stars pass right through without hitting anything. But the combined gravity of both groups pulls everything together, and the groups merge into a larger galaxy. This process repeats over and over. Small galaxies merge into medium ones. Medium ones merge into large ones. Large ones merge into giant ones. Over billions of years, small structures slowly build bigger ones. The Milky Way has undergone many mergers in its past. Astronomers can see the remains of old mergers in the structure of the galaxy, such as long streams of stars from dwarf galaxies torn apart and absorbed by the Milky Way billions of years ago. And in the future, the Milky Way will experience another major merger. The Andromeda Galaxy, the nearest large spiral galaxy, is moving toward us at about 110 kilometers per second. In about 4 to 5 billion years, the two galaxies will collide. The collision will take billions of years. First, they will pass through each other. Then gravity will pull them back, and they will collide again. After several passes, they will finally merge into a giant elliptical galaxy that might be called Milkomeda or Milkdromeda. During this process, the beautiful spiral shapes of both galaxies will be destroyed. Gas and dust will collide, compress, and trigger an intense burst of star formation. Millions of new stars will be born in a relatively short time. And at the center, the two supermassive black holes, one from the Milky Way and one from Andromeda, will orbit each other, slowly spiraling closer as they emit gravitational waves, until they eventually merge into an even larger black hole. But do not worry about the fate of Earth. Even though a galaxy collision sounds violent, the chance that the Sun or any star will collide directly with another star is extremely low. The distances between stars are simply too large. The solar system might be pushed to a new position in the merged galaxy, maybe farther out or closer to the center, but Earth and the other planets will continue orbiting the Sun as usual. Of course, by that time, roughly 4 billion years from now, life on Earth may have already ended, because the Sun naturally becomes hotter as it ages. But that is another story. The important point is that galaxies are not static, fixed structures. They live, grow, merge, and change over time. And this entire process, from the first stars to the giant galaxies we see today, has unfolded across 13.8 billion years of cosmic history. Every star you see in the night sky is part of that story. Every distant galaxy, seen through a telescope, is another chapter in that long history. And you, with the atoms in your body forged inside ancient stars, are an inseparable part of that story, too. Everything we can see, every star, every galaxy, every glowing cloud of gas, makes up only about 5% of the total mass energy of the universe. The remaining 95% is made of things we cannot see directly. 27% is dark matter. 68% is dark energy. And these two invisible components are shaping the fate of the entire universe. The first evidence for dark matter came in the 1930s, when astronomer Fritz Zwicky studied the motion of galaxies in the Coma cluster. He measured how fast the galaxies were moving through the cluster and calculated how much mass would be needed to keep them bound together by gravity. The results surprised him. The total mass of all the stars and gas visible in the cluster was not enough, not even close, to explain the speeds he observed. The galaxies were moving too fast. According to theory, the cluster should have flown apart long ago, with the galaxies scattering in all directions. But the cluster was still there, stable. Zwicky concluded that there must be some kind of invisible matter not emitting light, providing extra gravity to hold the cluster together. He called it dark matter. For decades, the idea was ignored or dismissed as speculation. But in the 1970s, astronomer Vera Rubin provided much stronger evidence when she studied the rotation speeds of spiral galaxies. When she measured how fast stars moved at different distances from a galaxy's center, she found something strange. According to Newton's laws, stars near the edges, far from the center, should move more slowly than stars closer in, similar to how planets farther from the sun move more slowly than inner planets. But observations showed that stars on the outskirts were moving at nearly the same speed as stars near the center. The rotation curve was flat instead of decreasing. The only way to explain this was that a large amount of invisible mass extended far beyond the visible disk of stars. This extra mass created additional gravitational pull that kept the outer stars moving faster than expected. And when astronomers studied many other galaxies, they found the same pattern. Most spiral galaxies have flat rotation curves, suggesting they are all surrounded by huge halos of dark matter. More evidence accumulated. Gravitational lensing, in which light from distant galaxies is bent as it passes through nearby clusters, showed that clusters contain far more mass than what we can see. The distribution of galaxies across the universe matches simulations only when dark matter is included. And the ripples in the CMB also require dark matter to explain the structures we observe. So, what is dark matter? We do not know for certain. But we do know some things about what it is not. It is not ordinary matter that is simply dim, like cold planets, brown dwarfs, or black holes. We can rule those out because they would leave detectable signatures that we do not see. Dark matter must be an entirely different kind of matter, possibly made of yet undiscovered particles we have never detected in Earth-based experiments. One leading candidate is called WIMPs, or weakly interacting massive particles. These are hypothetical, heavy particles that interact only through gravity and possibly the weak nuclear force, not through electromagnetism. Physicists have built extremely sensitive detectors deep underground to avoid interference from cosmic rays, hoping to catch a rare WIMP collision with an atomic nucleus. So far, no definitive detection has been made, even after decades of searching. Another candidate, which has become increasingly popular in recent years, is the axion. An axion is a hypothetical particle that is extremely light, possibly billions of times lighter than an electron. It was originally proposed to solve a problem in particle physics called the strong CP problem. But physicists later realized that if axions exist, they could have been produced in huge numbers in the early universe, making up enough mass to account for dark matter. What is interesting about axions is that they would form something called a Bose-Einstein condensate on a cosmic scale. Billions upon billions of axions would occupy the same quantum state, acting like one giant quantum wave instead of individual particles. And this axion wave could produce detectable effects. Experiments are now trying to find axions using microwave resonant cavities inside strong magnetic fields. If axions exist, they may convert into photons in the magnetic field, creating a faint signal that can be measured. So far, no definitive axion detection has occurred. But the search continues, and many physicists are optimistic that within the next few decades, we may finally discover what dark matter is. Whatever dark matter is made of, its role in the universe is clear. It forms the underlying framework, the invisible scaffolding that ordinary matter attaches to. As the early universe expanded and cooled, dark matter, because it does not interact with light, was able to begin clustering under gravity earlier than ordinary matter. While ordinary matter was still being pushed around by light, dark matter was unaffected and began forming structures. These dark matter structures created gravitational wells, regions of space where gravity was strong. When ordinary matter was finally released from the influence of light, it fell into these wells, gathered, and formed gas, stars, and galaxies. Without dark matter, galaxies and galaxy clusters might never have formed, or they would have taken far longer and looked very different from what we observe today. Dark matter is the invisible architect of the universe. It shapes the cosmic web that galaxies cling to. It holds galaxy clusters together. It determines how matter spreads out on the largest scales. And here we are, living on a small planet inside a galaxy held in place by a massive dark matter halo, something we cannot see but cannot deny. Now let's turn to something even more mysterious: dark energy. In the late 1990s, astronomers were measuring the expansion rate of the universe by observing Type 1a supernovae, the kind of exploding stars with consistent brightness that allow precise distance measurements. They expected to find that the universe was expanding but slowing down because gravity from all the matter in the cosmos should pull everything together. But what they found was the opposite. The universe was not just expanding, it was expanding faster and faster. The expansion rate was increasing over time. This made no sense. Gravity only pulls. It cannot push. It should slow expansion, not speed it up. Unless something else existed, a kind of unseen energy pushing space to expand faster. That something became known as dark energy. The discovery shocked the scientific world. Two independent research teams found the same result. And after many checks and confirmations, the scientific community accepted dark energy as real. The discovery earned the 2011 Nobel Prize in Physics. So, what is dark energy? We do not know. It is one of the biggest, perhaps the biggest, mysteries in modern physics. One possibility is that dark energy is vacuum energy, the intrinsic energy of empty space that we mentioned earlier. According to quantum mechanics, empty space has a baseline energy due to quantum fluctuations. And this energy has a strange property. It creates negative pressure, which acts as a repulsive force. If vacuum energy dominates, it would cause space to expand faster over time, which is exactly what we observe. But there is a massive problem. When physicists calculate the value of vacuum energy from quantum theory, they get a number that is larger than the observed value of dark energy by 120 orders of magnitude. It is the worst mismatch between theory and experiment in the history of physics. Another possibility is that dark energy is not constant, but a dynamic field called quintessence, which changes with time and space. But so far, we have no evidence that it changes. And there is another limit, even more subtle, that comes from quantum mechanics. In the quantum world, there is no absolute certainty, only probabilities. Heisenberg's uncertainty principle says that you cannot know precisely both the position and velocity of a particle at the same time. You cannot predict exactly the outcome of a quantum measurement before performing it. This is not a limitation of measurement techniques. This is a fundamental property of nature. Reality, at the quantum scale, is not deterministic, but probabilistic. And there are concepts in quantum mechanics even stranger, concepts that profoundly challenge human intuition. Think about a photon, a particle of light. In quantum mechanics, a photon is not a small particle flying through space like a bullet. It is also not a wave in a physical medium. A photon is an excitation of the quantum electromagnetic field, an entity spread throughout space with no definite position until it interacts with something. And in a sense, the quantum state of a photon can extend across the entire observable universe. Imagine a photon emitted from a distant star 13 billion years ago. For 13 billion years, this photon has traveled through space. But in the quantum framework, before it is absorbed, Its state is described by a wave function extending from the source star to the observation point. This wave function is a probabilistic description. It doesn't say where the photon is in the classical sense, but speaks of the probability of finding the photon at different positions if you perform a measurement. And this wave function can have correlations, connections, extending across enormous distances, billions of light years. Two parts of the same wave function, separated by half the universe, are still part of the same quantum entity. This violates our intuition about separate local objects. We are accustomed to the idea that a thing must be in a specific place, with clear boundaries. But quantum reality is not like that. And there is quantum entanglement, a phenomenon Einstein called spooky action at a distance. When two particles interact and then separate, their quantum states can remain linked. If you measure a property of the first particle, you immediately know the corresponding property of the second particle, no matter how far apart they are. This doesn't mean information travels faster than light. You can't use quantum entanglement to send signals. But it does mean that two entangled particles, even when separated by billions of light years, are still part of a single quantum system. They cannot be described independently. Reality is not local in the way we think. Parts of the universe can be connected in ways that don't fit with our classical intuition about separate objects in space. And there is a final reflection on the limits of perception. From the perspective of a photon, time does not pass. According to relativity, when you move at the speed of light, time dilates to infinity. Your clock stops. For a photon emitted from a star 13 billion light years away, from our perspective, it has traveled for 13 billion years. But from the photon's perspective, if we can speak of such a thing, the journey takes no time at all. Emission and absorption occur in the same instant according to the photon's experience. The entire 13 billion year history, from emission to absorption, is compressed into a single point in time from the photon's reference frame. If a photon could experience, it would experience the entire universe, from the beginning to the end of its journey, as a timeless instant. This shows that the concept of time, of past and future, of events happening in sequence, is relative. It depends on the observer's perspective, on their speed of movement, on the gravitational field around them. There is no absolute universal flow of time. Time is an aspect of physics that can bend, stretch, and even disappear under extreme conditions. And there may be perspectives, ways of experiencing the universe, that the human mind cannot grasp because we are constrained by biology, by the way our brains process information, by the evolutionary limits that created us to survive on a small planet, not to understand the entire universe. The universe may be more complex, stranger, and more diverse than anything the human mind can imagine. There may be aspects of reality that we can never understand, not because we're not intelligent enough, but because our cognitive structure is not designed to grasp them. Like an ant cannot understand a Beethoven symphony, not because it lacks intelligence, but because its brain doesn't have the necessary structures to process complex musical concepts. There may be aspects of the universe that for us, humans, lie beyond comprehension, not because we're not intelligent, but because we simply are not equipped to grasp them. But this is not a reason for sadness. This is a reminder of humility, that there is always more to learn, more mysteries to discover. And even with these limits, look how far we've come. We've discovered the Big Bang. We've mapped the radiation from the early universe. We've detected dark matter and dark energy. We've photographed black holes. We've understood the origin of the elements, the formation of stars and galaxies. These achievements are extraordinary, especially when we realize that we are just small creatures on a small planet, existing for a brief moment compared to the age of the universe. The universe is vaster, more ancient, and stranger than we can fully grasp. And there are parts of it we will never see, questions we will never be able to answer. But not knowing is not something to fear. It is an invitation to continue exploring, to continue being curious, to continue marveling at the complexity and beauty of all that exists. You are here on planet Earth, orbiting the Sun at 30 kilometers per second. The Sun orbits the center of the Milky Way at 220 kilometers per second. The Milky Way is moving in the flow of Laniakea, pulled by the Great Attractor and the Shapley supercluster. You are moving through space at hundreds of kilometers per second, but you don't feel it because everything around you is also moving in rhythm. You are surrounded by neutrinos from the Sun, from the first second of the universe, silently passing through you. You are lying in a sea of invisible dark matter. You are existing in space filled with dark energy that is pushing the universe to expand. Every breath you take connects you with trees, with the ocean, with the atmosphere of the planet. The oxygen you are inhaling was created in the hearts of stars billions of years ago. Every atom in your body, carbon, oxygen, nitrogen, calcium, iron, all were forged in the nuclear furnaces of stars. You are made from stardust. You are matter of the universe that has organized itself into a form that can contemplate itself. You are the universe experiencing itself. You are the way the universe is looking back at its past, contemplating its future, wondering about its nature. And in this moment, as you are relaxing, drifting into sleep, know that you are enveloped by the mystery and beauty of all that exists. Let your eyes close if they haven't already. Let your breathing become slower, deeper, gentler, more natural. No need to think about anything anymore. No need to remember anything. Just let your mind drift away like a leaf on water, gently, going nowhere. Just being there, drifting, settling down. If tomorrow, when you wake up, you feel a bit more deeply connected to the world, a bit more amazed by your existence, a bit more peaceful, realizing your place in this vast universe, then tonight's story has fulfilled its purpose. And if you want to share this piece with others, remember to hit the like button and subscribe to the channel so you don't miss the next journeys through science and the universe. But that can wait until tomorrow morning. For now, just sleep. Just rest. You are safe. You are exactly where you need to be. You are part of something ineffably magnificent, part of the universe continuing its story, continuing to explore, continuing to evolve. And in your sleep, the atoms in your body still vibrate. Your cells still function. Your heart still beats. Your breath still moves in and out. All part of the process of living, part of the cosmic flow. Sleep well. May you have beautiful dreams, perhaps of stars, of distant galaxies, of mysteries waiting to be discovered. And remember, when you open your eyes tomorrow morning, you will still be part of this wondrous universe, continuing its story through you, through every breath, through every thought, through every action. You matter. You are an indispensable part of all that exists. Sleep well. We will meet again in the next science stories. Rest deeply and let sleep come gently, peacefully, like light from distant stars, silently traveling through the cosmic darkness, carrying the secrets of time and space. Sleep well. Before we end, I would like to express my sincere thanks to pixabay.com for providing such wonderful free images that helped me create this video. If you found this content relaxing and enjoyable, don't forget to subscribe to the channel 5 Minutes Fall to Sleep. Give this video a like and leave a comment to let me know you're here. Your support is the motivation for me to keep creating more gentle and soothing content. And now, just relax, close your eyes, and let sleep gently come to you. Wishing you a very peaceful night's sleep.